Spillage, unfortunately I've seen quite a bit of spillage. It doesn't take much, as Don said earlier, right, to make this spill. The interesting thing here is that a lot of this stuff we could see. This water heater was spilling, and I could tell it was spilling before we went there, right? The guy putting this in didn't cause this when he put his torch on here. When the grommets are melted on the inside edge, it's because of spillage. And we need to make sure that that smoke goes up the chimney on all these houses that we work on. Here's an example of a really, really bad one. Hopefully none of you are involved in situations that look like this, but this was a clogged chimney and a depressurization issue in the building that caused this, so this was a double whammy. That's what a drafting water heater should look like, right? When the water heater's on, it should be able to pull that smoke from our smoke pen right up 360 degrees around that vent without any kind of issues. This was a more creative contractor. This was a CAS that had the furnace and the water heater in the same zone. The homeowner had done some renovations. They kind of penned in the furnace and air conditioner and the water heater in a kind of finished basement, if you will, and then put a solid door in that room. This caused like a -12 pressure imbalance in the building, and this was the not so creative way that the contractor used to try to fix the problem. He installed a board in here, and he didn't know how many holes he needed, so he taped up some of the holes. So if he needed more, he could add more. If he needed less. This heater would cycle on the limit switch when I went there probably within 2 minutes. So you could turn the heater on and bang, the heater was shutting off instantly. It wasn't in the air conditioning mode, but they probably would have froze the coil up in a couple minutes, right, of runtime. Wouldn't have taken it all. This is a much better way of fixing a pressure imbalance in the building. Again, if we have no returns and we have no ability to run returns to the rooms in the building, this is a down and dirty way to do it. It's very inexpensive. We cut a register on this side of the room, and we cut a register on the other side of the room. Not so good for light and noise, can definitely annoy people. There is some honeycomb baffling material you can put in here to slow light and noise down a little bit. I don't know that it's that effective, to be quite honest with you, but it's a very easy, cheap way to fix a pressure imbalance in the building when we have a spilling water heater or we're causing a lot of infiltration in the building. This is a little bit better way of doing it. We cut a high register on one side of the wall. We cut a low register on the other side of the wall. Air is able, again, to be able to go back to the air handler and not create that pressure imbalance in the building. Again, slightly better way to do it. Again, does transmit quite a bit of light and noise. This is a jump duct that goes up into the attic. They're cutting a ceiling register in the hallway ceiling. They're cutting another one in the bedroom, and they're putting an upside down flex duct. Again, this is pressure relief in that room. Air can get back to the unit and not cause a pressure imbalance in the building. Relatively inexpensive, but we're punching holes up into the attic, which isn't always the best thing. We really, really need to make sure that we're sealing up everything tightly when we do this kind of stuff. And you'd also be surprised at how big these ducts need to be. Build America program and stuff that BSC's published in the past, they have good guidance on this, depending on what kind of airflow is going into the room, how big a jump duct that you need so you can keep the pressure balances within range. So this would be makeup air for a kitchen hood. When the kitchen hood turns on, it's going to open up a motorized damper, depending on how much air we need to bring into the building. A lot of times they'll tie it into the air handling unit itself. That way it'll trip the thermostat pretty fast and turn on the heater or air conditioner. You do have to be careful with how much air that you bring into the air handler. You can shock the heat exchanger in the air handler and cause it to crack over time if you bring too much air into this. BSC, again, has some good guidance on that. About 7 to 10% is the max of airflow. So if we had a 1,000 CFM system, we probably wouldn't want to bring in more than 70 to 100 CFM of air. If we had a big air handler, we could bring in more air. But this is a way to, fix or interlock makeup air with a kitchen hood that's causing pressure imbalances in the building. How are we doing on time? Got a little bit of time? Okay, we'll try to get through this then. Air conditioning performance, this is another pet peeve of mine. I go in the field quite a few times on calls with contractors where they can't cool the building in the middle of the summertime, typically on the hot days. The first excuse I always get is that the manual J caused the problem. It's always the manual J. If I didn't do the manual J, I would have put the bigger system in, and I wouldn't have had a problem. And I've been with quite a few techs in the field these days, and they tell me the system's operating fine. It's operating exactly how it should be. They put refrigerant gauges on it. They did whatever magic they thought they did. But no one ever measures the system performance, I guess. And that's my big pet peeve. And it's pretty simple, and we're going to talk about how to do it today. This is the full drawn-out calculation. It's CFM times change in entropy times specific density times 60 times the air correction factor. It's a mouthful. This is actually what it works out to be. Because we live at sea level and we can do a mathematical shortcut for this 0.075 times 0.60, what it really amounts to is CFM times the change in entropy times 4.5. And if you really want to get crazy, you can take that number and divide the watt draw, so put an amp probe on the system and get the watt draw of the system and divide the two numbers, and you can get the EER of the system at that day and time. So what we really need to do is measure airflow first, right? We need a way of measuring CFM through the system. And I think the easiest way today to do that without buying a lot of tools, and most of us have manometers, is to measure the static pressure of the system and then look that up on the blower table for the piece of equipment. Again, with the phones that we're running around with today, I can usually look up the blower table within a couple minutes on my cell phone and figure out what the airflow is going to be based on the static pressure. Some of the newer equipment has thermostats or LED readouts on the board. We can measure airflow that way. And then there's the flow plate, which is the other way that I like, but it takes 10, 15 minutes to do that, and a lot of people don't like to waste that time. The second thing that we need for the entropy part of it is an accurate way of making wet bulb measurements. So a lot of people use digital sling psychrometers. I've had a lot of bad luck with them. In fact, when we go out in the field to teach air conditioning stuff, I tell everyone to bring theirs, and we always end up with 5 or 6 different measurements, which is disheartening when you spend $200-300 on a tool. You expect it to be accurate, and when 6 of us have the same tool or different tools and they all read a different measurement, it's not reassuring. Since then, I really like the thermocouple wrapped in cotton, and I'll show an example of that. To take static pressure measurements, we need to measure the static pressure before any external accessories. And people struggle with this a lot. We see a lot of this in new construction where they'll take it on the other side of the filter. The filter didn't come with this unit, so we need to measure static pressure in between the furnace and the filter. And that's where that location would be. This is a nice, easy, simple one. We also need to measure it before the air conditioning coil. So this is the furnace case, this is the air conditioning coil, but we need to take the static pressure below that coil to get an accurate reading. So we need the two of those, or the sum of those two numbers. This is another easy way to measure that, is to pull out the high limit switch. So this is a picture of a high limit switch. You can take these 2 screws out, put a piece of tape over that, and measure the static pressure in there if you don't want to drill any holes or don't have a good place to drill a hole. This can be a little bit of a scary location to drill a hole. If we drill far into here, we could hit a heat exchanger, and that would make for a really bad day. Anyway, that's what that looks like. That's what the high temperature switch looks like. If you're going to pull one of these out, you need to make sure that you shut off the power to the unit first. If not, if you touch any of this to a metal component, this is energized. If there's power running through the system, and you will blow the fuse in the board. I've learned this the hard way. This was one that I blew not too long ago. I thought I could pull it out, and I did not. I was unsuccessful. And it makes for a bad day when you don't have one of those there with you. This is an example of a blower chart. If we had 0.5 inches of external static pressure between those 2 holes, and we're on the medium-high wire, we'd be moving 820 CFM through the system. Again, in the past couple of years, I found it very easy, because of the internet today, to Google the model number and pull these manuals really fast in the field, and really haven't had a problem finding any of them. So if you measure the static pressure, we got the airflow, we're halfway home to measuring air conditioning system performance. And while you're at it, I always recommend that people measure pressure drop. So if we drill another hole here, we can measure the pressure drop across this filter. There's plenty of people that have upgraded the filters in their systems and are causing really reduced airflow because of the filters, and we can measure that really quickly if we're here and we're doing some of this work already. Same holds true here. Measuring one below the coil and one after the coil makes for quick work to see if that coil's restrictive or the coil's been clogged up. This would be the alternate way to measure airflow through the system using a flow plate. Again, I've had a lot of success with this, but it really depends on the filter configuration if this is going to be easy or hard. But it really doesn't take too long. I'd say about 10 minutes to measure airflow through a system, and it's a pretty accurate way to do it. This is the new way to do it. If you're lucky enough to have communicating high-tech new equipment, we can read it right through this thermostat. It's just a matter of knowing how to get to that screen in the thermostat and telling the system to run at that speed. This is old split capacitor PSC motor wiring. Again, you'd look at the wiring diagram to see what color is wired up to heating or cooling or whatever we're measuring. In this case, it would be cooling, and then which wire is hooked up to that. And this will tell you if it's running on low, medium, or high. Typically, black is the high speed from my experience. Digital sling cycrometer, again, we need a way of measuring wet bulb temperature to look up entropy. And I haven't had a lot of success with these tools. This, to me, has been a much easier way to measure it and much more reliable. This is a K-type thermocouple. You buy these for about 10 bucks. Obviously, you need a digital K-type tool. And this is kind of like shoelace. It has a hole in the middle of it, and this is made out of 100% cotton. If you're lucky enough to find cotton shoelaces, you could use those. If not, you can order this. It's made for this purpose. So this is used in commercial industrial applications to measure wet bulb temperatures in critical situations like food service and things like that. But anyway, it's just a matter of tying this around my K-type thermocouple and dipping it in water, and now I can get an accurate measurement on wet bulb, and I can check the accuracy of this really easy. I can put it in a cup of ice in an insulated cup, and I know right away if it's 32 degrees, I'm in the ballpark. This is an enthalpy chart. Again, we need that change in enthalpy to be able to measure air conditioning system performance. And this is the chart that you can use. Again, I don't use this anymore. I don't carry this paper around with me anymore. I use a psychometric chart and just plug in the temperatures. Anyway, we look our temperatures up. If it was 46.3 degrees, this would be our number, 18.32. We need to measure this on both sides of the system, so on the supply side of the system and the return side of the system, and subtract the two numbers from one another. And that's the difference or the change in enthalpy. Here's an example of it, 29.1 on one side, 23.53 on the other side, gives me a change of 5.57. If I was moving 800 CFM through the system, times 4.5 gives me 20,000 BTU output on my air conditioner. Again, if you're going on a service call for an air conditioner, the first thing you really want to know is the air conditioner working up to its rated capacity? If it's not working up to its rated capacity, then we need to start looking for other issues that we can fix. Questions? All right. Thank you very much.